Hi, and welcome back to the mole part 2, where we're going to use the mole now to determine certain characteristics of different compounds, okay? So the first thing we're going to look at is percent composition, which is exactly what it sounds like. It is how an element, how a compound is composed by percentage of each element. So the percent by mass of each element in the compound. So the formula is extremely simple. It's the same way you would find any percentage. It is part over the whole. So it's the mass of the element divided by the total mass of the compound or the sample. And just like any percent, we've got to multiply by 100, and that gives us the percent composition of the element. So for example, we want to find the percent composition of each element in sodium chloride. So of course, the formula for sodium chloride is NaCl. So I go to the periodic table to look up the molar mass of sodium and the molar mass of chlorine. Now I'm going to add those together to get the total mass of sodium chloride. And now I'm going to divide each individual mass by the total mass, multiply by 100, of course, because it's a percent. And I get that sodium chloride by mass is 39.34% sodium and 60.66% chlorine. So that means that every formula unit, and then even bigger, every crystal of sodium chloride is 30.34% sodium and 60.66% chlorine by mass. That's all percent composition is. It just tells us what's the mass makeup of a compound. So let's do a couple examples. Like always, I would suggest pause, try these on your own, and then come back and look at the answers. So the first one is carbon monoxide. So I look up on the periodic table, and carbon, 12.01, plus oxygen, which is 16, so that gives me 28.01, is the total mass. So now I'm going to divide each individual one by the total mass. And I'm going to multiply by 100, and I get 42.88% carbon and 57.12% oxygen. So that's the percent composition of carbon monoxide. Let's look at aluminum oxide. Now this time you got to be very careful because you have to take into account these subscripts. So all of you are capable of finding the average, or not the average, I'm sorry, all of you are capable of finding molar mass. So the molar mass of aluminum oxide is 101.96. So now I'm not going to take the singular mass of aluminum, which is 26.98, and divide it by the total because there's two aluminums. So I have to multiply that number by 2. So I get 53.96 divided by 101.96. And then for oxygen, I have 48 divided by 101.96. And so I get that this is 52.92% aluminum and 47.07% oxygen. All right, finally, we're given magnesium nitrate. Well, I can't begin to calculate molar mass or know how many atoms are of each element until I write the formula. So the formula for magnesium nitrate, magnesium is plus 2, nitrate is minus 1, so I need 2 of them to balance. When I calculate the molar mass, I get 148.3. So now I'm going to divide magnesium's mass by 148.3. I'm going to divide 2 times nitrogen, so 28 by 148.3. And then I'm going to divide oxygen. 2 times 3 is 6. So 6 times oxygen's mass is 96 divided by 148.3. And I'm going to get that magnesium nitrate is 16.39% magnesium. It is 18.88% nitrogen, and then 64.73% oxygen. Okay, so the next thing after percent composition that we're going to look at is something called the empirical and the molecular formula. So the empirical formula is the lowest reduced ratio of the atoms of each element in a compound. So what does that matter? Related compounds tend to have the same empirical formula, meaning they have the same ratio of atoms. The molecular formula, however, tells me actually how many atoms of each element I have in a compound. So for example, if we look at hydrogen peroxide, its molecular formula is H2O2 because in one molecule of hydrogen peroxide, we have 2 hydrogens and we have 2 oxygens. But its empirical formula, the lowest reduced, each of those is divisible by 2, so I get HO. So what that means is its ratio is 1 hydrogen to 1 oxygen, which is H2O2. There's still 1 oxygen for every 1 hydrogen. So any formula, any compound that has an empirical formula of HO has to have a 1-to-1 ratio of hydrogen to oxygen. So how do we determine the empirical formula of a substance? This is something that would be done in lab through chemical analysis, and then it would be calculated. So we can be given the percent composition of a substance and determine the empirical formula. And you may have learned this in regular chemistry, but a nice little rhyme that helps you remember the steps are percent to mass, mass to mole, divide by small, multiply or round till whole. So I like to add in that or round till whole because you'll see that sometimes we don't have to multiply through. A lot of times, actually, we don't have to multiply through. We just have to round the number, and you'll see what I mean. All right, so this is what a problem would look like. A compound of carbon, hydrogen, and oxygen is found to contain 54.5% carbon, 9.1% hydrogen, and 36.4% oxygen. Find the compound's empirical formula. Step 1 is percent to mass. This is real easy, y'all. You literally swap the percent sign with a gram sign. Given percent composition, always assume a 100 gram sample. So what's 54.5% of 100? 54.5. Okay, so we literally just swap out our percentages to grams. So step 1, percent to mass. Step 2 is mass to mole. How do we go from mass to moles? Molar mass. All right, so I'm going to divide each of those masses that I had from step 1 by their molar mass. I'm going to convert to moles, and I get how many moles of each element are in this compound. Now I got to find the ratio. So how do we find a ratio? We divide by the smallest number. So for this compound, the smallest number of moles is oxygen. So I'm going to divide each of them by the moles of oxygen. I get 1.99, 3.95, and 1. Well, in this case, we're going to be able to round those numbers because they're so close to the nearest whole number. So 1.99, of course, rounds to 2, 3.95 to 4, and then 1. So the empirical formula of this compound is C2H4O. We figured out that this compound has a ratio of 2 carbons for every 4 hydrogens for every 1 oxygen. That's what an empirical formula is. So any compound with this empirical formula would have to have that ratio 2 to 4 to 1. But wait, we can do more. So what if we have a compound, we determined its empirical formula, but maybe its actual molecular formula is something different? So we can find the molecular formula given the molar mass. So let's say we have a compound. We know it has the same empirical formula that we just determined, but its molar mass, so the mass of the whole molecule, is 132 grams per mole. What's its molecular formula? So I just said it has the same empirical formula as C2H4O. And now I want to figure out what its molecular formula is. So it told me the mass was 132. So now what I need to do is I need to figure out, okay, if its molecular mass was the same as its empirical, if its molecular formula is the same as its empirical formula, if I add up those masses, it would have a mass of 44.06. But it doesn't, it has 132. So now I'm going to divide 132 by 44.06, and I get 2.99, which is essentially 3. So what that tells me is that this molecular formula is 3 times the empirical formula's ratio. So I multiply all those subscripts by 3, and I get C6H12O3. So think about it. If you reduced C6H12O3 to its empirical, it would be C2H4O. Okay, so before I start this practice problem, I want to check to see who's actually listening to these videos. So if you're listening, I would like you to send me a remind message that says Happy Thursday. And if you do that, I will give you an extra credit point on an assignment. Yeah. So let's get started. A compound is found to have by mass 48.38% carbon, 8.12% hydrogen, and the rest oxygen. Well, we all know that percents have to add up to 100. So if we add these together and subtract from 100, we get that 43.5% is oxygen. Okay, so that was, now we have our percentages. So our first step is percent to mass. Super simple. We're literally just changing our percents to grams, because I'm assuming a 100 gram sample, meaning that all of these percents would just turn into the grams. Okay, so now I'm going to percent to mass, mass to moles. So I'm going to determine how many moles of each of these are present. So the way I would set this up, 43.5 grams of oxygen, for example, we look at the periodic table, 16 grams of oxygen is in 1 mole. So we're dividing by the molar mass. And so just because of space, I'm just going to write down dividing by the molar mass. And 16. So when I divide, I get the number of moles of each of them. 4.032, 2.72, and, oops, my bad, I jumped ahead. 8.12 divided by 1.01 is 8.04, and then this one is 2.72. So I have that many moles of carbon, this many moles of hydrogen, and this many moles of oxygen. So the third step, divide by small. Well, my oxygen is my smallest one. So I'm going to divide each of these by 2.72. And I get 1.48, 2.96, and of course 1. Now 1.48 is not close enough to the nearest whole number, but it is very close to 1.5. So this is going to round to 1.5, 3, and then of course 1. Now I can't have half an atom, right? So what I do is I multiply in order to get the lowest reduced number of whole numbers. So 1.5, of course, times 2 is equal to 3. So my numbers are 3, 6, and 2 when I multiply throughout by 2. So my final empirical formula is C3H6O2. And we can check our work because this is absolutely the lowest reduced ratio. I can't divide 3, 6, and 2 by anything and get a whole number. All right, molecular formula practice. A compound is known to have an empirical formula of CH and a molar mass of 78.11. What's its actual molecular formula? So 78.11 is what the actual molecule has a mass of. And then if it were just CH, it would have a mass of 12.01 plus 1.01, which is 13.02. So when I divide, I get like 5.99, which is essentially 6. So the actual molecule has a molecular formula of C6H6. So if we reduced that, it would be CH, which is an empirical formula. But the actual molecule is C6H6. But notice it retains that 1-to-1 ratio. The final thing we're going to look at is how we can actually determine the formulas for a hydrate. So as a reminder, a hydrate is just an ionic compound where water molecules are part of the structure. So like calcium chloride dihydrate means for every calcium chloride formula unit, there are 2 water molecules. So if we were in class, we might do a hydrate lab. You probably, well, I was going to say you would have done it in chemistry if you had it last semester. I guess not, but if you had chemistry before, you may have done a lab where you took a hydrate that looked something, maybe it was copper chloride, that would look like this, and it's blue, and you heated it, and it turned white because you drove all the water out, and then you weighed it, and you determined what the ratio of copper chloride to water. So we're going to look at an example of that. A 15.67 gram sample of a hydrate of magnesium carbonate was heated until it was completely dry. The mass was reduced to 7.58 grams. What's the formula of the hydrate? So first, we've got to write magnesium carbonate. Now, we got to determine how much water was taken off. So 15.6 minus 7.58 equals 8.02. So that means that the 7.58 grams is made up of entirely magnesium carbonate, and the 8.02 grams is made up of entirely water. So now I'm going to find the moles of each, just like I did in the other empirical formula problem. So I take their mass and convert them to moles. I'm going to then divide by the smallest one to get that whole number ratio, and I get 1 to 5. So I write the formula, magnesium carbonate, this dot just indicates to me that it's a hydrate, 5 waters. The name would be magnesium carbonate pentahydrate. So let's do one hydrate practice. So a hydrate of sodium carbonate has a mass of 4.31 grams before heating. So that means like in your little sample, it weighed 4.31 grams. After you heated it and all the water was evaporated off, the anhydrous, meaning no water, is found to be 3.22 grams. Determine the formula and write out the name. Okay, so my original sample had a mass of 4.31 grams. So that was my hydrate. And then when I was done, it weighed 3.22 grams. So then that means that's only the sodium carbonate. So when I subtract those two, I get 1.09 grams. So that's what's missing. So that's my water. So now I'm going to convert each of these to moles, which means I'm going to divide them by their molar mass. The molar mass of sodium carbonate is 105.99. Molar mass of water is 18.01. And I get 0.0304 moles of sodium carbonate. And I get 0.0605 moles of water. So I divide by the smallest one, which is 0.0304. Sorry, I'm out of room. And when I do that, I of course get 1 and 2. Sorry, this is a 0.0304. Sorry, divided by the smallest one. And I get 1 to 2. So that means my formula is Na2CO3, 2 waters, because I just determined the ratio was 1 to 2. So the name of that would be sodium carbonate dihydrate. Well, this has been another fabulous AP Chemistry lesson with Mrs. Wilkins. See you next time.